Right. So some we talked about in the lab, the intermolecular forces, the phase diagram, we're just kind of introduced to it, but now we're just going to go ahead and continue from here. But I think we'll probably get all the way through phase diagrams. But again, not a lot of math concerned here, all right, but just a lot of concepts, a lot of definitions going into Chapter 10 where we talk about intermolecular forces. So intermolecular forces are the attractions, right? The forces that are possible between molecules, right? The forces between molecules is that the attraction between this acetone molecule is different than the attraction between these two water molecules. So these are what we call, this is an intermolecular force, right? This is an intermolecular force. These are attractions that are between molecules, right? There's three that we're going to concentrate on. Dispersion forces, dipole-dipole interactions, as well as hydrogen bonding. Right. So there is a difference between intermolecular forces and intramolecular forces. Right. Intramolecular forces this is what holds our atoms together. Okay. So this covalent bond here, right? This is an intramolecular force, right? Covalent bond, these are intramolecular forces. These are the forces that keep this atom or this molecule together. And then we have intermolecular forces, which is the attraction, the forces between those. And it takes a certain amount of energy, right? A certain amount of kinetic energy to overcome and break this bond here, break this attraction, break this intermolecular force. So. The kinetic energy here, right? So here, kinetic energy is very low, right? This is colder, the temperature's low, not a lot of kinetic energy, and we have a high amount of intermolecular force occurring here that's keeping this all together. But as we add heat, right, we start to overcome those intermolecular forces. Right? This is now liquid. We add some more heat to it, and then we've really broken apart those intermolecular forces. So as temperature increases, the intermolecular forces decrease. Right? As we decrease that intermolecular force, that's because the temperature has been decreased. That kinetic energy has been decreased there. So the strengths of these different intermolecular forces, right? Again, dipole-dipole interactions, dispersion forces, or what we call, hydrogen bonding. They all have different strengths, some stronger than the others, and I think I mentioned this in the lab, right? So the strongest intermolecular force we have is going to be our hydrogen bonding, right? Those are going to be the strongest intermolecular force, followed by dipole-dipole interactions, then followed by dispersion forces. And collectively, you may hear, so instead of intermolecular force, you may hear the word of van der Waals forces, which means the same thing. So these are intermolecular forces. These are all van der Waals forces, okay? So those terms are just interchangeable. So if you hear van der Waals, we're talking about one of these three intermolecular forces here. Intramolecular forces are much stronger than intermolecular force. So this covalent bond, much stronger than this hydrogen bond. Now between the hydrogen bond and our dipole-dipole interaction, right? Well, the hydrogen bond is stronger than dipole-dipole interactions, right? But again, the covalent bond here, the bond between this carbon and this carbon, this covalent bond here, is stronger than either one of those intermolecular forces. Whether the substance is polar or non-polar, right? Partially negative, partially positive, polar and non-polar molecule. polar molecule, right? Because here we have this angle here, and then we have some net dipole that's going to be collected this way. And then we have stuff like this. So here, chloride, Cl2, Cl2. And then we have, what's considered nonpolar, right? So whether it's polar, whether it's nonpolar, they all contain intermolecular forces. Another one is this bond here. This is a non-polar bond. This is a non-polar bond. So even though there are two different elements, so here we have two different elements. Oxygen has a lot more electronegativity than hydrogen does. So this is considered to be a polar bond, and the molecule is also polar. Here's an example of a non-polar bond, a non-polar molecule. This is an example, another example. This is kind of our exception to the rule, is that the bond between carbon and hydrogen, the electronegativity difference between these two just isn't very large at all. They're pretty similar. So this bond is nonpolar, and this molecule is also nonpolar. Now, as far as acetone goes here, let me redraw acetone. So this molecule is polar simply because oxygen is more electronegative than carbon. So carbon here would be partially positive, and this is partially negative, attracted to this partially positive portion, and oxygen again partially negative. So we can get another acetone to make some dipole-dipole interaction here. But when we're talking about this here, right? Again, even though this is a polar molecule, the bond between carbon and hydrogen here is nonpolar. The bond between this carbon and this carbon is another nonpolar bond, right? So nonpolar bonds can exist in polar molecules. So nonpolar molecules can also have what we call dispersion forces. These are intermolecular forces. So dispersion forces are the weakest intermolecular force. So even though that this is nonpolar, that there is no polarity here, it's not partially positive or negative, it's not partially positive or negative. But if we think about a chlorine gas molecule, okay, or just any gas molecule itself, and they're always in motion, right? And the electrons here are constantly in motion. So what can happen, even though this is a nonpolar molecule, what can happen is because the electrons are always in motion, it doesn't take a lot to kind of jar one of those electrons to one side or the other. So as these electrons are moving around, it is possible to have this valence electron, let's see here. It is possible to have the electrons here, right, kind of shift one way. And as soon as it makes that slight shift, one of these becomes partially negative and one of them becomes partially positive. And that has a chain effect, right? Because this positive end is attracted to electrons, it's going to run into another chloride molecule that has electrons, but this one may not have, you know, any polarity just yet, but because this all of a sudden shifted, chain reaction is that now it causes this to pull the electrons this way, and we end up with another molecule like this. So this will actually induce a dipole-dipole interaction. They're temporary, right? They're just temporary dipoles. It's not a permanent dipole, right? This is a permanent dipole. It's always going to be polar, right? This nonpolar molecule can induce polarity, right? And cause some interaction there. So, but again, this is what we call an induced dipole. Right, is that we have some unequal distribution and we just cause a temporary dipole where we can have those attracted there. But again, whether it's an induced dipole interaction, they're still going to be considered dispersion forces, right? So,
is that like an example of that is like shaking the bond inside of a tube?
Shaking the bond?
Yeah, like shaking it inside the tube and it'll cause it to...
We wouldn't even have to shake it, right? If we take a look at this one here, right? We don't have to shake this, but what are we doing to it? We're heating it up, right? So if you know, there is you know, we can have chlorine as a liquid, right? And if we add enough heat to it, right, then we get chlorine gas. But that energy can cause those electrons to just kind of move out of place just a little bit and force this temporary dipole. Now, this molecule here, right? So we can have dispersion forces for this molecule, right? And here, if we did this, first, what I've drawn, is this a polar molecule or a non-polar molecule? Non-polar, because it has a bunch of carbons, hydrogens, right? So this is a non-polar molecule. Now, if we take a look at this small one here, small non-polar can cause a small temporary dipole. Large non-polar, well, because of the size of this and a mass of this, we have to think that the dispersion force here is stronger than this dispersion force here, simply because the size of it. Right? So because the size of it, right, larger molecules, heavier molecules can have a stronger dispersion force than lighter ones. All right? We're causing some temporary dipole here, but if we take a look at this, we're going to create a larger dipole, you know, induced dipole interaction here for those dispersion forces. Right? So we can definitely have larger, and we can see it here. We talked about melting point and boiling point. Melting point, boiling point, we can see them here. Going from solid to liquid, right? This would be our melting point, going from solid to liquid, and then our boiling point, going from liquid to gas, right? So melting point, boiling point. So as we're adding energy, we have to increase heat in order to overcome those dispersion forces. Right? So because this is a larger dispersion force than this one, well, this is going to require more heat in order to go from solid to liquid, or from liquid to boiling, to gas, right? So the freeze, or the melting point, the boiling point for this larger one would be greater than the melting point, boiling point, and we can see that here. So fluorine, chlorine, bromine, as we're going down that periodic table, right? As we're going down that periodic table, we're increasing the atomic radius, the molar mass is also increasing, and that's reflected here is that we need a higher temperature in order to overcome and break those intermolecular forces. So stronger dispersion forces lead to higher melting points, right? We can see it on this graph, but I did want to get to the next one over here. So, this is the one I've drawn up here. Right. So this is pentane over here. Then they have isopentane, and then they have neopentane. So I'm going to draw them a little bit different here. So here, this is, let's see, now all these hydrogens. So that we have neopentane, and then we're going to have isopentane. Yeah, well, okay, I think we're good. All right. When we have this molecule, pentane, interact with this other pentane molecule, it creates a very large surface area here, right? Large surface area for a larger dispersion force. But if we take this molecule and we put another one up to here, well, because of the way this looks, because of the structure, is we're losing surface area. So even though the mass is the same, this here, this is C5H12. This is also C5H12. This is also C5H12. So the molecular mass for all of these is identical, but this would have the strongest dispersion force. Right? Here we can kind of see some, I probably should have, let me see if I can redraw this. Yeah, let me redraw this one down here. We'll go this, 2, 4. I won't draw all the hydrogens out, but I think we can get a better idea here. Right. So here, pentane, 1, 2, 3, 4, 5 carbons in a row. This is isopentane, 1, 2, 3, well, 4 carbons in a row, and then I have this little branch sticking up here. So this has reduced that surface area by 1 carbon, and on top of that, now we have to get another one. This is kind of in the way, and kind of blocks anything over here from completely bonding with those dispersion forces, right? So this minimizes that. But then we get this structure here, which really minimizes. Maybe we can get another one over here, but because of the reduced surface area here, is that this would be the weakest dispersion force, even though they're all 5 carbons, 12 hydrogens, they have the same molar mass, is the shape of these can also affect those dispersion forces. Okay. Then we have dipole-dipole interactions, right? So dipole-dipole interactions are stronger than dispersion forces, right? And included in the dispersion forces was our induced dipole-dipole interactions, where we can force a temporary dipole, right? Dipole-dipole interactions are stronger than our dispersion forces, is that we use polar molecules that have some polarity. And there's a couple of ways that these can actually create those dipole-dipole interactions. So I have another slide here that'll show a couple of different ways that we can do that. Right. So, right, head on here is that here we can create some type of dipole interaction, and then we can also create dipole interactions this way. Right. So assuming we're looking at these, which dipole-dipole interaction would be stronger? Right. This one down here, right, is that this dipole-dipole interaction would be stronger between those two. So comparing polar and non-polar molecules that have similar molecular mass. Right? So dipole-dipole interactions also increase boiling point. Right? So which is going to have a higher boiling point? Is that here, right, is that chlorine is more electronegative than iodine, right? So this is partially negative, this is going to be partially positive, and then here we have this nonpolar molecule. This is going to create dispersion forces, this is going to create some dipole-dipole interaction, so these would have some stronger presence there, or some stronger, dipole-dipole interaction. Now, that's not always the case. I thought we had I had some graphs in here. Oh, I guess we can go over when we're looking at hydrogen bonding. Okay. So dipole-dipole interactions are definitely going to have a stronger effect as far as intermolecular forces go for that. And then lastly, we have what we consider hydrogen bonding. Right. In order to have hydrogen bonding, well, we need hydrogens. And again, just so that we're not confused, here's hydrogen. Is this a hydrogen bond? What kind of bond is this? It's a covalent bond. This, just because there's hydrogen here doesn't make this a hydrogen bond. This is a covalent bond. It's an intramolecular force, right? This covalent bond. The hydrogen bond, those are intermolecular forces, right? The attraction between this hydrogen and this oxygen, this creates a hydrogen bond, right? This here is simply just a covalent bond, right? So generally for hydrogen bonds, not all molecules, even though some molecules can contain hydrogen, simply containing hydrogen isn't enough for a hydrogen bond. Is that hydrogen bonding occurs with highly electronegative elements. Right? So if we're looking at this second period here, right, we're going to see oxygen. We're going to see nitrogen. We're going to see fluorine, right? These atoms here, these elements here, are highly electronegative, right? These elements here are highly electronegative. So even though I get a molecule like this, let's see. If we take a look at both of these molecules, both of them contain hydrogens, right? Versus This one will create hydrogen bonds. This will not create hydrogen bonds. When we talked about electronegativity early on in one of the other chapters, electronegativity decreases as we go across the periodic table, but it decreases faster going down the periodic table, and we start to lose electronegativity. So, highly electronegative element, not a highly electronegative element because it's lower down on the periodic table. So this would create some hydrogen bonds here. Now, because this is further down, so what happens, even though there's hydrogen here, what happens is, well, the atomic radius around phosphorus is much larger than nitrogen, right? So here, small atomic radius, phosphorus, right? Large atomic radius. And this large atomic radius is going to have what kind of intermolecular force? Right? Dispersion forces, right? So the larger the atomic radius here, right, is we're going to have dispersion forces. So if we take a look at this graph here, we're going to take a look at this one here, right? So we do see the boiling point going up, right? We're going down the periodic table here. We're going to follow this green one here. Or let's follow the red one here. So here's chlorine, and then right underneath chlorine is bromine, and then right underneath hydrogen here. So it seems that we kind of have a trend here, right? Iodine, bromine, chlorine. If we go with this trend, we would think that fluorine is right here. Okay? The reason that this boiling point is increasing is because the dispersion forces are getting larger with the atomic radius. But the boiling point for this is actually much higher. Is that this breaks that trend. It's not down here, it's up here because fluorine's a very highly electronegative element. Is that this is creating hydrogen bonds. Hydrogen bonds are much, much stronger than any of these dipole interactions or these dispersion forces that we could see here, right? So they're much stronger than that. So oxygen, fluorine, nitrogen are going to be creating hydrogen bonds, while the other ones are going to be creating dispersion forces or dipole interactions. Yeah.
Do these attractions mess with the shape of the molecules at all?
The attractions mess with the shape of the molecule. Not necessarily, because the shape of the molecule has to do with these electrons, these electrons, these electrons, not so much the polarity, right? Is that because this has three bonded molecules and one lone pair here, that's going to designate its shape, right? Is that here we're going to have something that's trigonal pyramidal, right? Versus something that is going to be something that's bent. So even though, if we take a look at water, right, is we're going to have hydrogen bonding occur here. But if we have this, let's go with, right, this is still going to be bent. And even though that this is going to be either some dipole interaction or dispersion force, it's still bent. Simply because it's got these electrons here, and then these two lone pairs. So this designates the shape of that. Does that make sense? Okay. You got another question, Maynard?
So when we're describing the shapes, we would use the same vocabulary we use from before?
But before, yeah, if we're describing the shapes of it, yes. All right. So that kind of covers the three intermolecular forces, dispersion forces, dipole interactions. And let me see, maybe we can come up with another example. I'm trying to see some other examples of dipole-dipole interactions. Oh, let's see, did they give us any examples here? All right. All right. I'm going to take a look at some properties of liquids, looking at adhesive forces, cohesive forces, talk about viscosity, surface tension, and some of the forces in here. So when we talk about stuff that's viscous, right, stuff that's very thick, even though they're liquid, they're very thick, right? Honey's very, very viscous, right? Is that it's not solid, it's very liquid, but the liquid is very, very thick. Right? Same thing with engine oil, right? Depending on engine oil is also thick, and we consider these to be highly viscous. So there's two forces working here. So here we have this spider web here, and we have two forces working here, adhesive and cohesive. So for cohesive, right? So we're looking at cohesive forces, right? This is what's holding, the cohesive forces is holding all the water molecules together, so we have this one droplet here, right? So we have this big droplet here, and cohesive forces are keeping that together, right? Here's our cohesive forces keeping that together. And then our adhesive forces are what's keeping this stuck to that spider web. Right? So this drop of water is stuck on the spider web by adhesive forces, but the water molecules that are being held together are cohesive forces.
When we think of cohesive forces, can we think of surface tension?
Yeah, we can think of surface tension in that way. Is that there's some there's enough hydrogen bonding there at the surface to keep those molecules. So yeah, I think you can consider the pretty similar. We're thinking the same way. So with surface tension, right, is that here we have this bug right on the edge of that right here. So right on the edge of that here, and this is what we call surface tension, right? So our cohesive force is right here, keeping these water molecules together. The weight of that bug here, this mosquito, whatever this bug is here, this is its leg right here. That's what we're kind of looking at right here. So this is the leg of that bug. And the weight of it is not heavy enough to overcome the hydrogen bonding that's occurring there. This is why they won't sink, right? But if I throw a rock in the water, where's the rock going? Is it going to stay at the top or is it going to sink? Obviously it's going to sink because the rock is heavy enough to overcome that surface tension, right? To break those cohesive forces in order to overcome those intermolecular forces, those hydrogen bonds that are keeping that together. Right? One of these is mercury, one of these is water, and we've seen this plenty of times. This is our meniscus that we get, and it's again those adhesive cohesive forces here that give us this different shape here, which is much different than mercury. If we put mercury in a test tube, we get this meniscus over here, right? Because there's different cohesive attractive forces from sticking to that piece of glass that we have there. And those also occur I'm trying to remember. I think was this the lab? I think we did the lab in here. Well, we talked about ions. Did we do that with the paper and that it went up and I think we heated it? Yeah, okay. So here, those cohesive and adhesive forces here, those hydrogen bonds, all of that occurs here. So water has an attraction over here, and the ethanol has an attraction into the paper towel. So this paper towel has cellulose fibers in there, right? And those cellulose fibers the water molecules and the ethanol. So this is ethanol here. So let me draw ethanol so that we're understanding here. So and actually, let me see if I can draw cellulose. So what do we notice about the cellulose that I've drawn here? There's a lot of what going on here? Right? You got hydrogen bonding that can occur with cellulose. So water molecules right? This is ethanol. So ethanol, hydrogen bonding, water, hydrogen bonding, cellulose, hydrogen bonding. So what happens here is we get this dry paper towel over here, and with the ethanol and water that are in wine, they're attracted to those cellulose fibers, right? So they can creep up there. But what's keeping the ethanol and the water up here is, well, it's the hydrogen bonding that's occurring between this and the cellulose. Right? So all of those will climb up to a certain amount here, right? But they can only climb so far, right? They won't climb up to, all the way because, again, the weight of all the water, the weight of all the ethanol, there's a certain limit before it just starts to break apart, and we just can't get it any higher. All right. So we've talked about adhesive, cohesive, viscosity. And then we're just going to take a look into some what we call phase transitions. So phase transitions occur when we go from solid to liquid, when we go from liquid to gas. And we're going to look at these intermolecular forces. We'll look at these phase changes. So here, when we go from solid, looks like we're going from liquid to solid, right? Melting and freezing. So when we go from solid to liquid, that's melting. And we go from liquid to solid, that's freezing. We can just think of some water there, right? Liquid water freezes into ice. Ice melts into water. Vaporization, condensation. Right? If I boil liquid water, it'll vaporize. And then we have clouds that will, as soon as they get cool enough, it'll rain, so we get condensation. So going from liquid to gas, vaporization, going from gas to liquid, we get condensation. And then at the very bottom here, at the very bottom, we have sublimation and deposition. So sublimation Sublimation, you saw that in the lab, right? This is when we're going to go from solid to gas. So we bypass that liquid phase and it goes strictly just from solid to gas, right? This is what we consider sublimation. And then the opposite happens here. When we go from the gas phase, bypass the liquid phase, and go straight to the solid phase, so that's considered deposition. Right? So sublimation, deposition is what we have here. So vaporization, liquids converted into gas. And in a closed container, before we move on here, right? In a closed container, right, is that the liquid and vapor come into equilibrium. I haven't built one myself, but it has been a goal of mine. I'm hoping to complete it next year. But I would really like to build one of those enclosed terrariums, right? Where they add, you know, some greenery in there, some moss in there. They add a few bugs in there. They spray some water in there, and the whole thing is sealed, right? And this occurs inside of those terrariums, right? Is that you'll always see some water droplets, right? Those liquid water droplets. You're always going to see some condensation, right? But there is some equilibrium of liquid and vapor in those terrariums, right? So, where are we? So, when we reach that equilibrium, right, the rate at which the liquid vaporizes is the same as it condensing, right? The same as we get as condensation. So, the liquid, right, in the container doesn't change after that. Is that if we have some closed container, right, so my water droplets here. This is my liquid phase, and then this is our liquid gas phase over here. Right? As soon as we reach our liquid, so here, before it comes to equilibrium, right, is that some of this has to evaporate, so that liquid level is going to go down. But after it reaches equilibrium, the amount of liquid is just going to be constant now. Right? So the amount of liquid, or amount of water that's in the gas phase, the amount of liquid that's in the liquid, or amount of water that's in the liquid phase, at equilibrium, those remain constant. We're not going to get this up and down surge of water, liquid water increasing and decreasing. So after some time, we reach equilibrium, and we create something that we call vapor pressure. Okay. Now, vapor pressure can occur even in an open system. Right? Is that if I had a beaker of water and I just place it over here, there is a very small vapor pressure just sitting over that liquid, right? Is that because of the temperature in this room, right, is the liquid water is going to contain some kinetic energy, and enough kinetic energy that at the surface, some of those molecules will convert into gas molecules, right? If we sealed it, then if we seal that beaker, then it would come to some equilibrium. Right? And then we'd have this constant vapor pressure here. And in an open system here, right, is that we have some small amount of vapor pressure up here because this is going to evaporate, right? And again, because of the temperature here, this will consistently evaporate until everything has been gone. So when I reach dynamic, I should have not drawn that picture, so we could have just used this, but here's our liquid here, right? And as it's increased, this one will actually show the vapor pressure increasing. So we put our liquid in here, and then there's really no vapor pressure in here. But after some time, we're going to get some of that liquid to evaporate, and we can see the vapor pressure building up. And then over here, this is when we reach equilibrium, and we can have some amount of vapor pressure. But these are, what's the name of these? The name of this is a manometer. Does it have it in here? I can't remember quite the name. I think it's not a barometer. I think it's a manometer in this system here that we have closed. But again, in a closed system there, we can determine what that vapor pressure is. So vapor pressure of any substance is independent of how much we have. So whether I have a beaker of water here, or whether I have a big tub of water here, the vapor pressure is the same, right? So it doesn't really depend on the volume. It's independent of how much volume I have. But the vapor pressure does depend on the substance itself. If I have a beaker of water sitting here, does water evaporate? We did that experiment on this. Did water evaporate very quickly or not when we were dunking it? Because we did stuff like with hexane. So here we did this with hexane, CH3. This is the one that evaporated the fastest. Right? This is the one that had the largest temperature change because it was evaporating the fastest. Versus water, which had a very small temperature change. Now, it had a small temperature change because there was hydrogen bonding occurring there, and hydrogen bonding is the highest or the strongest intermolecular force versus hexane. Right? Nonpolar molecule dispersion forces, those are very weak, so it caused a large temperature change. So even though it's not dependent on the volume, if I have a beaker of water and a beaker of hexane, the vapor pressure is higher in the hexane because it's evaporating faster. Right? Because these intermolecular forces are easily broken, is we're going to have a lot more in the gas phase at the surface. So we get a higher vapor pressure. So taking a look at these here, right? This hydrogen bonding, hydrogen bonding, hydrogen bonding. Here, well, we may have a little dipole interaction occurring here, but it's very symmetric, but we're definitely going to have some dispersion forces here. So as far as vapor pressure here, which one would have the highest vapor pressure? (25% chance to get it right. So ethanol is small, but it does contain some hydrogen bonding. So take a look at this, hydrogen bonding, hydrogen bonding, hydrogen bonding, dispersion forces. Which one's going to evaporate the fastest? The dispersion forces. And the faster it evaporates, the larger the vapor pressure is. So we're going to have a high vapor pressure here. And now we're talking about water here. We have hydrogen bonding here, but we do have this nonpolar tail here. Right? So the next one to evaporate the fastest, so we go ethanol with the highest vapor pressure. Here go into ethanol. And then we have between water and ethylene glycol. So here, one oxygen, two hydrogens, two oxygens, two hydrogens. Is that the vapor pressure is going to be water, and then the lowest vapor pressure would be ethylene glycol. I don't know if you know what if you've ever seen ethylene glycol is actually pretty viscous, right? It's very thick here. So ethylene glycol would have the lowest vapor pressure, followed by water, followed by ethanol, followed by diethyl ether, right? So vapor pressure increases with increasing temperature. Beaker of water. So this water has some vapor pressure right here. Right? So there's some vapor pressure here. This is going to evaporate very slowly. But if I want to increase the vapor pressure, right? Let's just add some heat to this, right? This is my fire. This looks horrible. This is supposed to be fire. Actually, it's pretty good. It's almost lifelike. Right? 4K vision right here. It's like an OLED monitor, I swear. But if we add some heat to this, right, more of this is going to evaporate, which means we're going to have a higher vapor pressure. So if we increase the temperature, right, if we add some kinetic energy, so an increase in temperature is going to increase our vapor pressure. So water here, 24 millimeters of mercury at 25 degrees, but the vapor pressure is 92 millimeters mercury if we double that temperature, right, if we increase it to 50 degrees. So just some things to know about liquid or about vapor pressure and temperature. All right. as we add kinetic energy, right, we see this kinetic energy increasing, low temperature, high temperature, and then we see that shift over here. And then there's also just some minimum amount of kinetic energy to reach that phase change. Going from solid to liquid, going from liquid to gas, right? Is that there's a certain amount, a minimum amount of kinetic energy that's needed to make that transition. But as we increase the temperature, we're adding that kinetic energy to it. So when the vapor pressure of a liquid increases enough to the external atmosphere, the liquid reaches its boiling point. So when this vapor pressure here reaches 696 millimeters of mercury, so when this vapor pressure here increases to 695 millimeters of mercury, that's when it's reached its boiling point, right? As we have to add enough heat to this, enough kinetic energy, where we can evaporate this and get this boiling. So when those vapor pressures are equal to each other. All right, variations in atmospheric pressure. So top of Mount Everest, air pressure is very low, right? Standing over at the in the beach, vapor or atmospheric pressures is 1 atmosphere compared to the atmospheric pressure up in Mount Everest. So the effect this has on it, right? If we know that if we can get this to equal atmospheric pressure, we can reach the boiling point. So at increased elevation, we have a lower air pressure, which means that this boiling point is going to be lower, right? So temperature, so elevation, right? Elevation has an effect on boiling points. Is that here we can get away with not boiling. Here we don't need to be at 100 degrees Celsius in order to boil water. We need to be at like 98 or 99 degrees in order for water to boil, because we're at 4,000 feet. Versus if we're standing at the beach, no, I need 100 degrees Celsius in order to boil water. Yes, ma'am.
See, we were in outer space.
Mm-hmm.
There was just free-flowing water. Would it turn into ice first, or would it boil first?
Oh, good question. In a vacuum, yeah, you know what? In a vacuum, I've never had that question. I'll have an answer for you next time. But that's a great question, because there's no air in space, so there's no atmospheric pressure there. If we happen to just put water out there, would it boil away, or would it crystallize? The temperature would be absolutely freezing, but we would have no pressure. Yeah, good question. I'll come back to you with that one.
Would that just only be with water, or is that with solvents as well?
With solvents as well.
Okay.
Yeah. So let's say this was hexane,
Yeah.
right? Hexane evaporates very quickly, right? But if we reduce the temperature, we can reduce that vapor pressure, right? Is that we don't need to get to 100 degrees to evaporate or to boil hexane, but it has a pretty low boiling point. But yeah, we could, because we see it just go from, it'll evaporate at room temperature.
But just like the different altitudes, like being up here,
Mhm.
it'll boil faster than you would down.
Then it would down, yeah, absolutely. Then it would down, if you're at Santa Monica or Long Beach, is that there's going to be a slight temperature difference in reaching that boiling point. Yeah, absolutely. So, because of these different temperatures, we get to learn the Clausius-Clapeyron equation and how temperature and vapor pressure relates when we have two different pressures and two different temperatures. So when we're using this equation, you don't have to memorize this. I'm going to give it to you on the exam, or exam 4, so there's no need to memorize it. You just need to learn how to use it. So here, because we're talking about enthalpy, is that our R constant is going to be 8.314 joules per mole Kelvin, right? Not 0.08206, is that pressure is used for the ideal gas law, right? So for here, temperature has to be in Kelvin, but this is going to be our R constant, and then our enthalpy of vaporization is going to be in joules. In order to use that R constant. So let me say there should be some problems here. It's one or two problems here. So at 20 degrees Celsius, the vapor pressure of ethanol is 5.95 kilopascals, and at 63.5 degrees Celsius, its vapor pressure is 53.3 kilopascals. Use this information to estimate the enthalpy, how much energy is required for it to vaporize, right? Our enthalpy of vaporization. So this is going to require some work here. All right. One, you can plug everything in that you need and try and do the algebra. Or we can rearrange this before we try and do our algebra. If this is what we're looking for here, right? If I take this and divide it by 1 over T1 minus 1 over T2, I also have to do the same thing over here. 1 over T1 minus 1 over T2. This would go away and this would go away. Does everybody see that? That's just some algebra. Next, in order to get rid of this, well, I have to times this over here, but I also have to times it by over here. So these two would go away. Does everybody see that? So just some algebra that we have to do here. But then we get our final equation here. I'm going to clean this up a little bit here. We're going to say R times the natural log P2 over P1 over 1 over T1 minus 1 over T2 is equal to this enthalpy that we need. So all I did was just kind of clean this up a little bit, but here's our equation here. So we know what R is. We just have to decipher what first initial final and initial final here. And for this equation, it actually doesn't matter which one you pick, as long as you keep them both together. So when I get word problems like this, using this equation, it's happened myself, is that I lose track of what's 1 and what's 2. So I generally would just write everything down. At 20 degrees Celsius, the pressure is going to be 5.95 kilopascals, and we're going to have 63.5 degrees Celsius. Its vapor pressure is going to be 53.3 kilopascals. And we have 63.5 degrees Celsius. Nope, let me write that temperature above here. Oh, wait a minute. Nope, we didn't need this. There we go. Okay, I see. 63.C. We have to keep track of this. This is where I'm going to say, it doesn't really matter. The answer actually comes out to be the same. It's either this is P1 and this is T1, this is P2, this is T2, but it also works out. If this is going to be P1 and T1, then this needs to be P2, T2. But when you put it into this equation, it doesn't matter which one is P1. We just have to be consistent. Right. So here, let's go ahead and make this, this is going to be P1. Oh, that's T1. T1, and this is equal to P1, which means this is going to be T2, and this is going to be P2. So as long as I have these, I can figure that out, yes.
For R, is it 0.80206?
No, for R, because enthalpy is in joules, right, is we're going to use 8.314 joules per mole Kelvin, right? That's what we want, because enthalpy is going to be in joules. So now that we know this information, we just kind of have to keep things straight. So here we are. We're going to put 8.314 joules per mole Kelvin, and we're going to multiply that by the natural log of P2, 5.95, over P1, 53.3, and I'm going to divide that by 1 over T1, 63.5, minus 1 over T2, which is 20 degrees. Oh, and this has to be in Kelvin. So let's go 273.15 plus. All right, I'm going to calculate this with you. It may take a minute or two to calculate it, but let's calculate this. And use natural log, don't use log. Pretty large number. Anybody get anything yet?
Yeah, the units is joules per mole.
Joules per mole is our units, yeah. These are going to be, here, this is unitless, right? The kilopascals cancel out the kilopascals, so those are unitless. And then this is going to be in Kelvin, this is going to be in Kelvin. That cancels this, so our answer is in joules.
So 41336.04.
Yep, or 42 kilojoules per mole, right? So, 41 kilojoules per mole. Same answer, right? 41,000 joules per mole, or 41 kilojoules per mole. But again, this is how we use this equation here. Enthalpy of vaporization. So vaporization is an endothermic process. Is that when we go from liquid to solid, right? So ice freezing is an exothermic process. So the reverse of that, right? Ice melting is an endothermic process, right? I can't melt the ice until I add some heat into that, right? If I don't add heat into it, it's not going to melt. If I don't add heat into water, right, it's not going to boil, it's not going to vaporize. So, right, whenever, right, you leave a swimming pool, get out of the shower, is that water starts to beat up here, right? So this is a cooling effect. Right? When you get out of the pool, sometimes you get a little bit cold, right? Because this water that has to evaporate off of you, right? This water that has to evaporate off of you is an endothermic process, right? Your body is adding heat to these little water molecules that are here, right? These little water droplets. These water droplets are taking heat away from you. And this is why we get the little shivers when you get out of a hot shower, get out of the pool, when you're getting out of the coming in from the beach, right? Is because that water has to evaporate off of you. And when it does evaporate, if you're not drying off anyways, right? If that water is evaporating for you, it's an endothermic process, and it's using your body heat in order to evaporate. Oh, let's see. Do we have a problem here? Okay. Oh, this is a word problem. I think we can get to this. So just another calculation here, but nothing too horrible. So our body, the way our body is cooled by evaporation, the water and sweat in very hot climates, we can lose 1.5 liters of sweat per day, right? So, obviously if it's hot, we are sweating and that wet water evaporates, but that's a way for our bodies to cool down is when we sweat, right? Is that we don't want to get overheated, we do need to cool down, so when we sweat, that sweat is then evaporated, endothermic process, and then it cools us down. So how much heat is required to evaporate 1 liter of water at 37 degrees Celsius? And how much heat is required for that? And we have 43.46 kilojoules per mole. So here, I'm just going to write some information down. Our enthalpy of vaporization is equal to 43.46 kilojoules per mole. We have 1.5 liters of water, so 1.5 liters of water. We know the density of water. Density of water, well, we know this. Well, maybe not the density of water. I don't think we need the density of water, but what we do need to know is that 1 gram, right? We should know this. 1 gram is equal to 1 milliliter, right? So how many milliliters in a liter? 1,000, right? So in 1 liter, there's 1,000 milliliters, which means that there are 1,000 grams in 1 liter. If 1 gram is 1 milliliter, 1,000 grams is 1 liter. So we can use that information here. So let's convert liters into grams by simply saying 1 liter is equal to 1,000 grams. And now because I need moles, well, water is 18.02 grams per mole. So here, water, grams, we're going to put 18.02 grams of water for every mole of water. These units cancel these units, this unit cancels this unit. And now that I have moles of water, we can simply go 43.46 kilojoules per mole of water, and those units cancel out. So just a little dimensional analysis problem that we have here. And then we can just simply calculate this. Let me see here. 1.5 times 1,000 divided by 18 times 43.46. And we get 3,621 kilojoules. So this is how much energy, right? How much energy that would require, or how much heat that would require in order to evaporate 1.5 liters. Let's do the other one there real quick here. How much heat's required to evaporate 100 grams of, so 100.0 grams of ammonia. Well, this is already in grams. It's not in liters, but it's already in grams, so I think we just need the molar mass for this. So ammonia is 14, 15, 16, so 17.04 grams per mole of ammonia. And do they give us some? Yep, 4.8 is our enthalpy. So 4.8 kilojoules per mole. And I think that cancels everything. Yep. So that was just a little bit simpler. We didn't need to convert liters into grams. So we get 100 divided by 17.04 times 4.81. And we get 28 kilojoules. So 28 kilojoules. Okay. So calculations when we're talking about enthalpy of vaporization. I don't know if we can see it very clearly here. Here's ice. Again, we can't see that very clearly. I don't even know if I can see that very clearly. Any clearer now? Maybe this is like negative 10 degrees or something, I don't know. But this is ice here, right? And as the ice starts to melt here, so this is ice, not melting, just solid ice. And then as it begins to melt, this is 0 degrees Celsius. And that's our phase change, right? We need to be at 0 degrees Celsius in order for water to turn to liquid, liquid to turn to water, but that's that phase change there. And as we continue melting, this is 0 degrees. The ice is half melted, but we're still at 0 degrees, right? So even though it's melting, the water is not getting any warmer. It doesn't get any warmer until all of that ice has been melted. So until all of it's been melted, so at that phase boundary, going from liquid or solid to liquid, until it's completely changed, is that there is no temperature change. But the reason it's not changing temperature, there is a reason, and it has to do with those intermolecular forces, right? All the kinetic energy that's being added into going from solid to liquid is being used not to raise the temperature, but it's being used to break those intermolecular forces, right? So all of that energy, right, all of that kinetic energy is being used to break the intermolecular forces here so that it becomes liquid water. And it won't raise anything until after that. So we can see it just as at our phase boundaries. So that even happens when water is evaporated. Right? So here's our phase change here, where we don't see that. And then up at the very top as well. Right? When it goes from liquid to gas, is that that water in the beaker is not going to be more than 100 degrees Celsius. Because all the energy that's being used at this boiling point over here is being used to break those hydrogen bonds to get gas. And then it's also reversed, right? So if we go from gas to liquid, right? This phase change here, this transition here, is that we don't get any temperature decrease until all of it's been converted into liquid. So this here will show us sublimation. So here we go. So going from solids to liquid, we call that fusion, but this is just melting here. So melting from solid to liquid and then going from liquid to gas. And there's a certain amount of energy that's required there. Right? Certain amount of energy to melt, certain amount of energy to vaporize. But when we're going from solid to gas, right? Solid to gas, it still requires the same amount of energy. Right? Still the same amount of energy to melt it and to vaporize it. So both of those energies together combine to make that enthalpy for sublimation. Right? So it's not any more, it's not any less. Looks like we didn't get to fluor. I think we're going to cut it off here. Well, maybe, let me see how much. Yeah, we'll talk about phase changes. Yeah, we'll talk about that the next lecture, so we're good. Exam tomorrow. Exam 3.